So I just want to go towards random effects model today. Uh, the rest of the lectures already uploaded, and then this sort of a brief primer to why we do a random effects model. And so I'll discuss various examples and then motivate why we do this random effects model. So let's say way back in the class, like 3-4 weeks back, we started discussing ANOVA, that is this analysis of variance model. And mainly we used it for the cases when we want to understand some sort of categorical variable. Right? So for example, let's say, um, um, let's give you an example. We want to understand time taken to heal versus let's say, from a surgery versus patient's eating habits. So let's say the question you understand is to understand time taken to heal after, let's say, operation. And we want to understand its relationship on the patient's eating habit. Let's say. Right. So what do you do? Let's say you assume a patient has you classify the patient into, let's say, 3 groups. Let's say, so you put the eating habits as into 3 groups. Let's say a person has good eating habits, uh, in normal eating habits, let's say, like, and then let's say bad eating habits or something like this. Or you call them as 0, 1, and 2. So this is what you group everybody in, and then you look at time taken to heal them. Time taken to heal. Let's say make a specific, maybe a specific operation, which you might like kidney operation or something like that. Let's say it's a specific surgery. This is one example we have studied quite often. So we have 3 groups, and we want to know if the time as a treatment is different across the groups. Right? So one thing I didn't perhaps emphasize, uh, uh, analysis of variance is just the first generalization of the 2 sample t-test. You have 2 populations, and you want to test different means. So this is like a generalization of the 2 sample t-test. In 2 sample t-tests, you have 2 populations, you assume they were normal, and you want to know if the 2 means are the same or not. So you have to test x bar minus y bar divided by square root of sample variances, and then you saw a t-statistic, and you decide if they were the same or not. Here, as a variance, the number of groups can be large. And the way we modeled this thing in the previous classes was that we said, fine, what we will do is, let me write this in. So what model do we take? We took this following linear model. We said let yi, for each group, we had a yij variable, right? So that's the response. That is okay. And this was given by a fixed mean plus an alpha I effect of the group in some sense, and then plus an error term, which is a normal distribution. So epsilon ij was normal with mean 0 and variance sigma square. And we had this long time back, I had said this idea about identifiability. So I would just also identify for estimating correctly, I would just say summation alpha I is equal to 0. And let's say we had R here, I had three groups. So let's say I had R groups, so the I equal to 1 to R. Right. And we would have Ni populations in 1 less than equal to I less than equal to R. And here, let's say uh, each group had Ni observations. And this is what we did. And then we did many things with this. Let's go line by line what all we did. So one is that this was a model. And the first thing was we should try to fit the model, right? We try to fit the model and estimate the parameters. Okay. Then post-fitting, after finding all the sum of squares of treatment and errors and so on and so forth, we did some inferences. We did some testing for the main effect, right? And then we had various ideas of inferences and how to test things and so on and so forth. And that's how we closed discussion on this first example that we did. So this was the what we would call as the one-way analysis of variance. So I'll just call this as, I'll just write this down. This ended a discussion on what, I haven't written all the gory details of statistics, but this was the model we had in mind, and we did this, we call this the one-way analysis of variance. Very good. Then now, in the next, so let me just pause for a second so you can take a look at it. And just recall what all test statistics we took and how do we get them and so on. So you can go back to week 9 or week 8 and then come to this. The next thing we did was we said, okay, fine. No, suppose you have a disease. Okay, let's say you have a heart problem. Your heart valves are blocked, let's say, and you need a heart replacement surgery, let's say, or a heart transplant, or even a bypass. So now you try and see after the bypass how long the patient has to stay in the hospital, and you try and see if it determines on the weight of the person, on amount of days in the hospital, and how long they were under this sort of pressure of the disease and stuff. Let's say we do this second example. Let's call this two-way analysis variance. So we call this example 2. So I'll just call it so I just call it heart bypass surgery, let's say. Right, so let's say after heart bypass surgery, we want to know if the time of stay in the hospital depends on multiple factors. Let's say it depends on, let's say, weight gain, duration of treatment, and so forth. So depends on, let's say, weight gain, and let's say they were having treatment before so heart bypass doesn't come immediately. You get treated before that with normal medication. So let's say weight gain, and then let's just say duration of treatment before the surgery, right? And then number of days in the hospital is what you want to understand. This is what. So what you do, you would again, in this case, you have factors like what? You have factors like the number of days they spend in the hospital. That's one factor that you have, right? That's one factor, right? And then the one that's what you want to understand. Then days, let's say duration of hospital stay. Let's say duration of hospital stay. Then this is the weight, let's say. So this I would just call it like so I want to understand weight gain. So let's say again I'll put 3 levels. Let's say they didn't gain weight, they gain some weight, they gain a lot of weight. So let's say 3 levels, let's say. Then so 3 levels. And let's say the other one is the how long they were under treatment. So let's say treatment duration, I'll call it. So they were under blood thinners for quite some time, or I don't know, or they suddenly came into the hospital with any treatment, you know. So let's say this time. So let's say here we put 2 levels, 0 and 1, let's say, short and then long. Right. So we have data set. So now here, this is the next generation of the previous one. So you have more than one grouping. So you're trying to understand days with regard to two groups, weight and treatment duration. So you have two groups. And you have some factors in the first group, some factors in the second group. Right? So there are how would you model this? This here the model was the following. Here we went and modeled it in the following way. We said what we would do is we would say we had y sub I, j, and k, right? And this was mu, the overall effect. And then each group, let's say you have alpha I, right? And then plus beta j. And then you could have this, I just call it, for lack of a better terminology, alpha beta ij. That is between these two guys, you have an effect. And then plus you have an error, epsilon I, j, k. So what all did we assume? We assume that epsilon I, j, k were normal 0. They're all independent, normal with mean 0 and some variance sigma squared, and typically assume that the fixed variance for all the groups. So we'd assume there are R groups in the first factor, right? So we'd assume typically this one less than equal to I less than equal to R in the first factor, and let's say there are let's say there are M groups in the second factor, and each observation was Nij, right? So the Nij observations. Yeah. So this is how we would run the whole thing. And in our case, we had here in this case, we had R equal to 3, right? This is the first group. And here M equal to 2. The first factor and second factor, and we had two groups. Sorry, I'm sorry. I misspoke about the groups and the factors. So first factor was weight, second factor was treatment duration, and typically we thought of this as let's go back here. We typically thought of this as this we modeled here as sorry about that. This is what we thought of as interaction effects. This is the interaction effect. Maybe you gain weight because of treatment, or you already gain weight because of the whole thing. You don't understand this thing. So typically, you want to understand if there was an interaction effect was there or not. That inference you would do. So this is something you test for. This is one thing. Very cool. And then again, you would have all these parameterization factors. You would say that for identifiability, you would always have summation I equal to 1 to R, alpha is 0. That's the same as summation j equal to 1 to M, beta j was 0. And then you would also have the other guys as well. So the sums over, sorry, the sum over, if you take the alpha beta ij over I, or you take alpha beta over j, you'd all have them to be for identifiable. Right, very nice. And then we do the same thing. We would fit the model, we'd make inferences, and test. So that broadly was the theme of this thing which we called as the two-way analysis. Two-way analysis. So I'll let the two examples for you to stay a little bit. Then now after this, I will just so I'd like you to think a little bit about how we understood the analysis of this, what tests we did, and what statistics we did for a couple of seconds. I'll try and get to the. Okay, now I'll try to go to this random effects model where we'll try to understand uh, when to use random effects and when to use fixed effects like we're using here. So these here in these models on both sides, this alpha I was a fixed effect. So there was no randomness in it. We thought it could be measured correctly and precisely. So and there was no sort of error in measuring alpha I. So I knew exactly what alpha I is. And here also there's no sort of error in measuring alpha I and beta J. So let me give you a bunch of examples before I sort of do any modeling. And then for each example, we'll see how does one proceed with statistical analysis of this whole thing. Very good. So the first example that I want to do is a basic sort of example from any study, let's say. Let's do a simple example. So now let me start this motivation for random effects. Suppose we were interested in this. There are many studies on this. You can check if you just look at any research papers available in the library or even articles on the web. Typically, people understand is well understood right now effects of smoking on blood pressure. Let's say. So you want to understand this. So here, what would you do? You would first pick a bunch of smokers, non-smokers, go and measure treatments from them, go and measure blood pressure from them, and then see if they're different. That's one way of doing it. So let's say we perform the following experiment. So we go to every participant in this trial and we take 5 repeated measurements at hourly intervals. Okay? So we take 5 repeated measurements at hourly intervals. For each participant. Right. So that's what we do. So how will we do this? So we'll group people into 2 parts. Let's say on the left hand side we group all the smokers. Let's say so on the left hand side all smokers. Let's say we have smokers on this side, and let's say we have 5 of them. A, B, C, and D, or 4 of them, let's say. And then we take observations of them. Let's say 1, 2, 3, 4, and 5. Right? So, 5 observations of them, and then or 4 observations. For 4 people, we do 5 observations each. Okay, this is what we have. So and then so these are what's called repeat measurements, right? So you're going and doing every hourly, you're doing repeat measurements. And then you go and sample for non-smokers. Let's call them. Let's call them non-smokers. So non-smokers we have. And again, we have A, B, C, D. We have 4 people, and then we do again the same repeat measurements for that. So let's copy that. This is what we have. So now let's see what all can we infer before doing any analysis. Let's just see how this is the data you'll have of measurements. Now let's try and see something about the observations. So the first thing you can always observe is that each of these columns, right? These columns, they're all observations from the same participant. Okay? So they're observations. So an important remark to keep in mind. They're observations from the same participant. And in some sense, they are not statistically independent. So therefore, not statistically independent. So you have to keep that in mind. It depends on the person, and in a dependent way. So all those things. And the other is that, of course, there is one random effect that you have sort of by the sampling of people. So there is a random effect of let's say patient ID. So there are you've picked a patient in a sort of and this is not quite replication. It's sort of it could depend on A, B, C, and D in some way, and so on. So this is one way of doing the experiment. You go to everybody and do this. The next procedure, I'll do the same. So this is procedure 1. So let's call it procedure 1. And procedure 2, I will do the following. What I'll do is we'll employ 2 nurses, right? So let's say nurse 1 or 2. Nurse 1 will go and measure from smokers. And nurse 2 will measure one measurement from non-smokers. So let's say this is measured by nurse 1, all measured by nurse 1. And this is all measured by nurse. So now here, what's happening is that your measurements, of course, the same equipment, perhaps the equipment has no sort of thing. The random effect comes from the nurse. The nurse might be inducing a random effect. This is one experiment that I like you to keep in mind. And let's see if I can show you the double window so you can just see it for a second. So the 2 is one experiment, and in one case I do repeated measurements, same person, and let's say I do it in a methodical way with the same instrument, same nurse. But there's independence because of the person involved. The second one, I do the same thing, but I have 2 people doing the measurements, and they could induce a random effect in the model. So the idea is that the dependency is sort of introduced, and the yij's may not be independent by h. This is example one. So in the previous examples that we had, let's say in this in the first one, in this one, or even in this one, the in both examples, the categorical variables are well defined categories, right? So for example, like this is a well defined category, there's no problem, and so is this. So is weight and treatment. They are well defined categories. So there's really but in this cases, in the one that I've described just now, the category is like a subject, so it's also prone to sort of variation. And so this is because you're doing repeated measurements on the one individual in this case, right? Or the group effect that you have in mind for nurse or whatever you do. And that's best taught of random population. Okay. So let me do another example, and then after that I'll set up the theory properly and I'll close for the day. And the rest of the things, next lectures will be available online. You can look at them. So the next example that I like to keep in mind is, like, let's say we all are interested in, let's say, beetroot juice, and we want to know the potassium content in beetroot juice. So if you want to know, we want to understand the potassium content in beetroot juice. And there are some bunch of companies that are making it. So beetroot juice, let's say in India, among all brands. Right. So the questions will be how much potassium is there, right? That's the first thing you want to understand. The second thing you want to understand is that does it vary across brands? Right? There are two things you would like to immediately sort of pick up when you're understanding this potassium content. So let's say there are six. Let's say we sample. So we go and do the experiment. So we go experiment. We take 6 brands, right, of beetroot juice. So you go to the market and just find 6 brands, and then what you do is you choose for each brand. You choose eight bottles. Choose 8 bottles. Let's say we also do the same thing. Let's say all these companies, let's say 8 packets. Let's say 8 1-liter packets. Of each brand. Then you want to understand what's the mean potassium content and does it vary across brand too. So in this case, the brands are like each brand is like the individual, right? Is like the individual that we had in mind. So each brand is sort of has a dependency in what it produces. You can say factory perhaps, and like the individual, and these 8 are your form of repeated measurements. And that's the formal connection. So just to summarize, you have to understand these things. So the way one should do this is that, let's see. So when to use random effects. So when to use random effects. So I have not told you how to model random effects. I'll come to in the last page. But these effects, how do you model them, or when to use them? So when do you think it's fixed? When do you think it's random? So one thing is that a group effect is random if we think of the levels we observe in the group are to be samples from a larger population. Okay, so we say a group effect, we think of a group effect to be random can be thought to be random if we believe that what we're observing belong to samples from a larger population. If we believe the observations are samples from a larger population. One. The next thing is like for example, if you're collecting, so let's do example. Let's say, so how do you think of a group as random? So what I mean by group? So let's do an example. You're collecting data from different brands or a certain store, let's say, different store, let's say. So you're collecting data, some data that we have, say, from different districts of India, let's say, for example. So here the districts may be thought of as random in something because there's a sort of a each person may have a random effect. Or let's say you're surveying students on different campuses on different universities, right? In different universities. And each university you would think has a random effect, right? So it's something like keep in mind. So this is the basis of random effects. So I just again do a small recap before I start. I just state the model and I close with the day. So you can either use this effect of the nurse or effect of the brand and as models for the individual repeat measurements, or this nurse having a random effect on the measurements, or these type of observations that we have, right? So from different districts, you go collect data. Each is going to be random in terms of how it behaves. And here we go and do at every university. And then just keep in mind, keep always the two models we had in the beginning. There's example 1 and example 2, right? So in both these cases, we had these alpha i's and beta j's kind of fixed. They were known quantities. There was no error in them. There was nobody interfering in how we were going to measure them. It was well understood that they were correct. So what we do here is that, so I'll just do the simple one-way random effect, and then we can do the two-way one yourself, or in the lecture notes it'll come. So one-way random effects model. So what you do is you go the same way you want. You take yij is equal to mu plus alpha I plus epsilon ij. And then let's say you again have R groups, so 1 less than I less than R, and you have Ni observations in each group. Right? Or let's even here I'll take fixed observations, probably better. It's a little simpler. Then in the fixed effects model, we always took epsilon ij to be normal zero sigma square. That's all we did, right? And then we assumed for Estimability, we assume summation alpha I to be 0. We set epsilon ij to be normal mean 0 with sigma star and independent. And here what you'll do is in this particular setting for the random effects model, let me call the random effects instead of the model, I'll also assume that the alpha i's are not fixed, they're random. They have there's some error in measurement or some effect that that we introduced in the model, and this I'll also assume to be normal with some mean 0 and variance some sigma square alpha. Again, independent across the i's. And now you'll have to develop a particular system by which how you understand this model. So you'll have to model the variance, you'll have to fit the model, and you'll have to balance the design and do the testing. So for this particular thing, you'll have to again fit the model. It's no more sort of because mu plus everything. This is random. It's not a fixed effect, so it's a random effect. And then you have to understand how to test for how to model the variance. And then you have to also understand how to test for them. So that's the objective of the random effects model. Again, once you write down the specific statistics, the tests are available. There'll be a classical F test, and then you can sort of run with the whole thing. You can do inferences on mu because alpha is random now, and then once you okay, that's all I wanted to say today. Maybe I'll stop.